Now, mostly since it's interesting and not so much because it will be on the exam, I'll wrap up by saying a little bit about nuclear fusion, nuclear fission, and some of the medical effects and uses of radioactive isotopes. Because of the popularity of the Chernobyl miniseries, I'm going to guess that at least a few of you are familiar with the fact that radioactive uranium isotopes are used in many countries to generate electricity. This has important advantages, notably, as a non-fossil fuel source of energy, nuclear power generates almost no carbon dioxide or other gases that contribute to global warming. Nuclear power generation relies on a process called nuclear fission, where uranium-235 atoms are struck by neutrons, causing them to split apart into two smaller nuclei, which releases a large amount of energy. Because the process also releases, on average, about 3 neutrons for each fission, which can then go on to strike other uranium atoms, the process can be self-sustaining. This is known as a nuclear chain reaction. Despite the source of energy coming from nuclear fission as opposed to, say, chemical energy from burning fossil fuels, the basic principle of operation of a nuclear power plant isn't all that different from other power plants. The heat generated by the nuclear fission is used to convert water into steam, which is used to spin a turbine which generates electricity. The US is the world leader in nuclear power generation in absolute terms, although notably very few nuclear power plants have been built over the last 40 years due to increased public opposition to nuclear power, magnified by accidents such as the 3 Mile Island incident in Pennsylvania in 1979, the Chernobyl incident in Ukraine in 1986, and the Fukushima incident in Japan in 2011. That said, by almost any objective measure, nuclear power has a much better safety record than any other major source of electricity production. Even ignoring fossil fuels' contribution to climate change, burning coal, oil, or natural gas all produce air pollution byproducts that are responsible for far more deaths each year in the United States alone than have ever been killed in all nuclear accidents around the world in its entire history. Still, nuclear accidents have happened and people have been killed in several of them, so it would still be nice if we could generate nuclear power in an even safer form. Also, uranium isn't an especially common element in Earth's crust, so it would be great if a different source could be found. As it turns out, there is a different process of nuclear energy generation that meets both these criteria. Nuclear fusion involves combining the nuclei of light atoms to produce new, heavier nuclei with a release of energy that's even larger than the amount of energy released per atom by nuclear fission. Nuclear fusion is actually what powers the sun, which, if you really think about it, means that solar power is actually just another form of nuclear power. So what's the catch? Why aren't we already replacing every other source of electricity with nuclear fusion reactors? They don't melt down, they use very cheap and common elements, hydrogen, they are more efficient than nuclear fission, and unlike fission, they don't create radioactive waste. Unfortunately, in order for nuclear fusion to occur, we have to bring 2 positively charged nuclei extremely close together. This is really hard to do. Getting enough nuclei to do this to produce a sustainable reaction is thought to require a temperature of 40 million Kelvin. That's certainly possible inside the sun, but here on Earth it's quite the challenge. To put that temperature in perspective, the element with the highest melting point, carbon, melts at a temperature below 4,000 Kelvin. Still, this is an active area of research, and some progress has been made, including the first laboratory nuclear fusion reaction that was able to produce more energy than it consumed, being performed in 2014 at the Lawrence Livermore National Lab in California. Let's briefly discuss how radiation can be measured. The most common device for making measurement of radioactive particles is a Geiger counter, which operates by generating a small electric current each time an alpha, beta, or gamma particle hits a detector. There are different units for quantifying radioactivity, which measure different things. Some units are simply used to count how many radioactive decay particles are produced per second, while others attempt to measure the total amount of energy absorbed per kilogram of body tissue, or to directly quantify the amount of actual tissue damage in any radioactivity exposure. The most common unit of radiation exposure, the sievert, falls into this last category. As you probably know, and as I just implied on the last slide, exposure to radioactivity can be harmful to living organisms, including humans. The exact details are complicated, of course. For instance, alpha particles carry more energy than other types of radiation, but they're also very bad at penetrating any further into the body than the outer layers of skin. Gamma rays, on the other hand, carry less energy per particle than alpha or beta particles, but are much more capable of penetrating body tissues to cause damage. Besides simply causing damage, there are also different considerations for radiation exposure when it comes to short and long-term effects. The long-term effect of high radiation exposure, cancer, is something that most people already know about. but long-term radiation exposure can also cause other health issues, including cardiovascular disease and other common causes of death that can, and usually are, linked to causes other than radioactivity. The short-term effect of high radiation exposure depends on the dose, and everyone is exposed to some radiation every day simply due to radioactive isotopes in the environment as well as inside the body itself. But at much higher doses of radiation than normal, symptoms of radiation sickness can develop. At the lower end, this can be mostly asymptomatic or cause a temporary drop in white blood cell count. Higher doses can produce extended nausea, vomiting, diarrhea, or even hemorrhaging. In the worst cases, death may occur within a few days to a few weeks or months. Radiation isn't all bad news from a medical perspective, though. Radioactive isotopes can be used in controlled ways to treat certain medical conditions, including destruction of tumor cells or treatment of certain thyroid conditions, for instance. And another major application of radioactive isotopes in medicine is in imaging. Certain radioactive elements can concentrate in certain tissues or organs, allowing the inside of the body to be imaged without the need for exploratory surgery. Some of these techniques and their associated isotopes are listed here. You can see PET scans, which I mentioned earlier, where positron emissions are detected. Another important imaging technique uses technetium isotopes to scan the brain or other organs. Okay, hopefully this shorter coverage of Chapter 20 has at least been interesting. Like I said, some of this stuff at the end was covered just because it's interesting or important to know about as a member of society, but I'm not going to put any of it on the test. As always, let me know if you have questions about the information here or in the homework problems, and please stay safe.